Alright, let's talk about normal distribution. In this video, we talk about the basic concept and characteristics of normal distribution. So let's get started. Let's take a close look at the normal distribution. We can use this distribution to describe our data and draw statistical inferences about how well our process is working. Once we have a clear understanding of the normal distribution, we'll see how we can use this to answer questions like what is probability that a phone will not meet specifications of weight, and how likely is the sample mean to be close to the process mean. Here is a histogram of the data we collect. Most of the phones have weights that are close to the target of 145 grams. The distribution appears symmetric and unimodal. The classic distribution used to describe data with these properties is a normal distribution. We've already seen normal distributions in connection with the sampling distribution of the mean. A normal distribution has a symmetric bell shape and is centered at the mean. The normal distribution uses a continuous curve to describe probabilities rather than focusing on the probability of any individual value, such as a phone weight of exactly 144 grams. We look at the probability that the data will fall in some interval, such as between 143.5 and 146.5 grams. This probability is represented by the area under the curve within the interval. Here, the area is 0.87, which means that 87% of the phones have weight between 143.5 and 146.5 grams. This curve is called a probability density curve. A probability density curve is a curve that shows how probabilities are distributed over the possible values of a continuous variable. Total area under a probability density curve is always 1 because the total probability of all possible values is 1 or 100%. As you can imagine, there are many different variations of the normal curve, wide ones and narrow ones, and they can be centered at any point on our scales, but we can precisely define each normal distribution by two parameters, its mean and its standard deviation. The mean is central value of the distribution, and it determines the location of the curve on the graph. The curve is symmetric about the mean. The spread of the curve is determined by the standard deviation. A normal distribution with a small standard deviation has little variability, so its curve is narrow. A normal distribution with a large standard deviation has a greater variability, so its curve is wider. Let's review. A normal distribution is a bell-shaped curve that is symmetric about the mean. The normal distribution is identified by two parameters, the mean and the standard deviation. We are concerned about the width of the force on our line because we must ensure that they are manufactured within the specifications. That is, there is a range of values that are centered around 145 grams that are still acceptable phone weight. Any phone with a weight that is outside the acceptable range is considered defective. Based on extensive data, the standard deviation of phone weight is estimated to be 1.018 if the distribution is normal with a mean of 145 grams. So what percentage of phone weight should be within specifications? The normal distribution has a very interesting and useful property regardless of the mean and standard deviation. The area with one standard deviation around the mean is always the same for every normal distribution. 68.26% of the distribution is contained within one standard deviation. One standard deviation, this one sigma. A similar property holds for any number of standard deviation. For all normal curve, 95.45% of the distribution is contained within two standard deviation of the mean. This one, the two standard deviation, and 99.73 lies within three standard deviations. This one is three standard deviation, three sigma. Because of this property, it is useful to talk about a value from a normal distribution in terms of the number of standard deviations it is from the mean. This expression is called the z-score or z-value. The z-score gives the distance of any value from the mean in terms of standard deviation units. Let's take a look at how to use these scores. Suppose we are interested in the proportion of phones that fall within 2 grams of the target weight of 145 grams. So how can we find the probability that our values will fall within the range? The standard deviation of the phone weight is 1.018. So 2 gram is 1.964 standard deviation units. The z-scores for phone weight 143 and 147 are minus 1964 and 1.964. For any normal distribution, the probability of the z-score is between minus 1.964 and 1.964 is the same using software such as Minitab or JMP. We find that this probability is 0.9505. So if the process follows a normal distribution with mean 145 and standard deviation 1.018, we've assumed for these calculations 95.05% of our phone weights are within 2 grams of 145 gram target. The remaining 4.05% 4.95% 95% are our outside of this range. These scores for different points on this graph. So remember, this score is expressed as the point distance from the mean in standard deviation units. Let's review. The normal distribution has a useful property regardless of the mean and standard deviation. The area within any given number of standard deviations around the mean is always the same. For example, for every normal distribution, 68.26% of the distribution is contained within one standard deviation of the mean. We also learned that the z-score gives the distance of any value from the mean in terms of standard deviation units. This calculation can give us a sense of the probability that data will fall within a certain range. We want to study the performance of the phone manufacturing process. We draw a sample of 5 phones from each hour's production and measure their weight. We most recent sample has mean of 145.5 grams and a standard deviation of 0.351. Let's recall that we are trying to accomplish by sampling. We want to use statistics such as the sample mean to draw conclusions about population parameters such as the process mean. The target for the mean phone's weight is 145 grams, but we observe a sample mean of 145.5 grams. So is this uh, within the typical sample to sample variation we should expect if the process is on target, or does the latest sample provide evidence that the process mean has shifted? And if it has shifted, so what is the process mean now? Let's try to answer these questions using what we know about sampling distribution and normal probabilities. For samples taken from a normal population, the distribution of the sample mean is also normal. The sampling distribution is centered at the population mean. The standard deviation of the sampling distribution of the mean, the standard error, is equal to the population standard deviation divided by the square root of the sample size. If we take sample standard deviation as our best estimate of the population standard deviation, the standard error of the sample mean is about 0.157. We know that for any normal distribution, the probability of falling within two standard deviations of the true mean is approximately 95%. If the standard error is 0.157, the probability of taking a sample in which the sample mean is within 0.314 or two standard deviations of the process mean is 95%. So if the process mean is on target of 145 grams, we could expect to see the sample mean between 144.686 and 145.314 grams in 95% of all samples of 5 phones. The sample mean of 145.5 observed by us has a z-score of about 3.18, the sample mean would be within 3.18 standard errors of the process mean with probability in 99.79% of samples. So sample mean of 145.5 is not within the typical variation we would expect if the process were on target. This sample does in fact provide evidence that the process mean has shifted away from 145 grams. It looks like the phone's weight are no longer on target. So what is the process mean now? We said that for 95% of samples, the sample mean is within two standard errors of the process mean. So with a standard error of 0.157, we can be highly confident that the process mean is within 0.314 grams of 145.5, somewhere in the interval 145.086 and 145.814. In these calculations, we use a standard error of 0.157 to calculate the standard error. We divided the sample standard deviation by the square root of the sample size. Technically, however, the standard error is equal to the population's standard deviation divided by the square root of the sample size. We assume that the sample standard deviation and population standard deviation were the same. So how safe is this assumption? Thus, as the sample mean is not likely to be exactly equal to the population mean, the sample standard deviation is unlikely to be equal to the population standard deviation, depending on depending on whether we have overestimated or underestimated the population standard deviation. We may have calculated a z-score that is too large or too small. So how can we answer our questions about the process mean given our uncertainty about the standard error? We can use another distribution, the t-distribution, to compute the probabilities about the sample mean. The number of sample standard errors between the sample mean and the population mean follows a t-distribution. The shape of the distribution is similar to the normal distribution of the 2z score, but with a greater spread due to the uncertainty about the standard deviation. A t-distribution is a distribution of the number of the sample standard errors between the sample mean and the population mean. The t-distribution applies to random samples from a normal distribution. There is a different t-distribution for each sample size used to compute the sample standard deviation. We refer to this different t-distribution in terms of degrees of freedom. The degrees of freedom are equal to the sample size minus 1. As the degrees of freedom increase, the t-distribution gets closer and closer to the distribution of the 2z score. Let's see how we can adjust our conclusions to account for the fact that 0.351 was the sample standard deviation and 0.157 was the sample standard error. What's the probability that the sample mean is within two sample standard errors of the two process mean? With a sample of 5 phones, we'll need a t-distribution with 4 degrees of freedom. The probability of a sample mean is within two sample standard errors of the population mean is only about 88.4%. 88.4%. So if the process mean is 145, we can expect only 88.4% of sample means to fall within two sample standard errors of 145. We found that the sample mean of 145.5 grams was about 3.18 sample standard errors from 145. Based on the t-distribution with 4 degrees of freedom, the probability of sample mean being 3.18 sample standard errors of the population mean is about 96.65%. So we can still conclude that a sample mean of 145.5 is outside the typical range of variation we would expect if the process was on target. The sample statistics still provide evidence that the process mean is not 145 grams. So how precisely can we estimate the new process mean? Based on the t-distribution with 4 degrees of freedom, we know that 96.65% of samples of 5 phones, the sample mean should be within 3.18 sample standard errors of the population mean. Multiplying 3.18 by the sample standard errors of 0.157, we get 0.5. So we get the 0.5. Okay, here 0.5. So we can be confident that the process mean is between 145 and 146 grams. Although we are convinced that the mean phone weight has increased, we can't be very sure that it has increased by much. We'll probably want to collect more data to get more precise estimate. Let's review. We can apply what we've learned about normal probabilities and the sampling distribution of the mean to make inferences about a population mean. For example, in about 95% of samples, the sample mean is within two standard errors of the population mean. So we can determine whether a specific value of population mean is plausible given a sample, or we can estimate the population mean to be within two standard errors of the sample mean. Because we must the estimate the standard error based on the data, we should adjust our probability calculation using the distribution with the approximate degrees of freedom. Thank you for listening. In the next lesson, we'll talk about the hypothesis test and confidence intervals.